Good day, Professor Alexander. Fancy seeing you here at the University of Cape Town Film Studios. What brings you here?
Well, Professor Boyshausen, probably exactly the same reason as why you are here, and that is to talk about concrete.
That is true, but our audience probably wants to know why the two of us keep talking about this great stuff that has been around for millennia. Why is it still so important to modern society?
It's a good question, Hans, and I can tell you why. Concrete after water is the most used substance on the planet. Each person on the planet actually accounts for about 1 cubic meter of this stuff every year. So it's used in huge quantities. And if you look around you, all of our infrastructure, bridges, roads, dams, tunnels, whatever, all of these are built largely out of concrete in our infrastructure. So there are plenty of reasons for using this material. It's very versatile, it's easily applied, and it generally has good performance. But one of the main challenges of existing concrete structures is premature deterioration due to corrosion of the reinforcing steel. We also need to talk about that.
And that is one of the main reasons why we need to keep talking about concrete. As engineers, it is our professional duty to use the planet's available resources in a sustainable manner. For concrete, this includes designing and building structures with sufficient durability. In the last 2 to 3 decades, a lot of attention has been placed on the durability of concrete, which in South Africa has led to the introduction of the Durability Index approach. Mark, you were one of the driving forces behind the Durability Index approach. Can you tell us in a nutshell how it works?
Well, I wasn't by any means the only one, but yes, I did have a lot to do with it. And this durability index approach is based on the notion that to achieve durability in our concrete structures, we need suitable design procedures and quality assurance or quality control measures, which must account for the composition of the concrete on the one hand and the way that it is put in place, in other words, the construction side of it. So the test methods that we use and that have been developed here within South Africa include the oxygen permeability test and the chloride conductivity test. And these have both been used extensively in South Africa for research and in engineering practice.
Let's focus a bit on the Oxygen Permeability Index test, the OPI test, which has been used, for example, for design and specification of our civil infrastructure, our national road infrastructure in South Africa. The OPI value of a concrete relates to its resistance against carbonation. Carbonation is one of the mechanisms by which reinforced concrete structures deteriorate, because carbonation can cause corrosion of the reinforcing steel. And having a measure, a test method, to characterize the concrete's resistance against deterioration allows us to identify and quantify the various parameters that can affect the durability of our structures.
Exactly, Hans, and that is what we did in a recent study in which we applied probabilistic modeling to determine the factors that influence the carbonation of concrete and hence influence the potential durability of our infrastructure.
So, Mark, what is this probabilistic modeling approach all about? How does it work?
Well, this probabilistic modeling approach is all about the probability of something happening. In other words, also risk. And it's similar to what happens in structural design where we use a reliability approach. And it essentially incorporates durability models or deterioration models, which in our case relate to carbonation. In other words, the probability that carbonation progresses into the concrete at a certain rate can then be predicted based on the likelihood of those various influencing factors occurring.
So which factors are we talking about?
There are 2 sets of factors that we need to think about, Hans. The first one is the environment. In other words, for example, the amount of carbon dioxide in the air, which as we know is increasing all the time, and also the humidity, the temperature, and these environmental factors. The second major set of factors is about the concrete itself. So, for example, the type of cement that is used in the concrete, the cover to the steel, and also the microstructure of the concrete.
And the microstructure of the concrete is characterized by the OPI test, which we mentioned earlier.
Yes.
That's awesome. Let's look at some of the modeling results that we have achieved. For this comparison, we have assumed a reference case where the concrete has 25 millimeters of cover depth to the steel and an OPI value reflecting average concrete quality. In this graph, which relates the expected or modeled service life to the cement content in the concrete, we can see that the cement content has little influence on the durability of the structure. This is one of the reasons why we should never use cement content as a proxy for concrete durability. As expected, the ambient carbon dioxide concentration has a huge influence on the expected service life of the structure, as you can see in this particular graph. This correlation also allows us to look at the influence of the land use on durability. Here, the most severe exposure conditions are, of course, those with high carbon dioxide concentrations, such as industrial areas, parkades, and road tunnels. When we couple the ambient carbon dioxide concentrations with typical values of relative humidity, we can compare the expected service life of concrete structures for the various provinces in South Africa.
As you can see, we are lucky that we are situated in Cape Town. In other words, our structures might last longer. However, here in Cape Town, we have problems related to reinforcement corrosion because of chloride ingress from the ocean. But that is the topic of another presentation, and we won't take it further today. What is still interesting to consider in another reference model is the influence of cover depth on durability. In this diagram, you can see quite clearly that a higher cover depth, for example 50 millimeters, gives us much better durability or service life. In other words, in this diagram, that is expressed through a lower probability of durability failure. We should just speak a bit about durability failure. In this case, it's not about a structure collapsing, it's about a structure becoming unserviceable, for example, excessive cracking, staining, rusting, and things like that.
Of equal importance is the quality of the concrete, here expressed with the OPI value. And this, of course, explains the purpose of the test. So, Professor Alexander, what are we doing with all this knowledge on probabilistic modeling, carbonation prediction, OPI values, and all that?
Well, Hans, as we have seen, we need to understand the various factors that influence concrete durability. Luckily, we have the tools to do so now. I believe that further information will be found in our publication, but for now, we can conclude the following. Durability of concrete structures is of major importance for our built environment. It influences national budgets for infrastructure provision and also has high implications for sustainability and the use of resources. So, Professor Boyshausen, how do we design our concrete structures for improved durability?
Well, Mark, as we have seen, we need to consider the right combination of cover depth and concrete quality, depending on the prevailing exposure conditions. And we can use the OPI test to do this in the design process. Thank you for watching.
If you want to know more, you can find us in Cape Town or on the internet.